Howdy, everyone. Thank you for joining us here on another afternoon virtual tour of outer space. My name is Josh. I have the special privilege of coming to your house from my house here in not that sunny South San Francisco. I'm a member of the Morrison Planetarium team at the California Academy of Sciences, and we are trying to send our programming to you while we are all under shelter in place. And this is just one of the several programs we are sending out into the ether for you to enjoy. This one is a little special, though, because this is a program you can actually do for yourself. We're using a really cool software called OpenSpace. If you want to check it out, head to the OpenSpaceProject.org, and they can give you some really cool guidance on how to download it, install it, and check it out yourself. But this is planetarium software for everyone. And it's actually something we're working on getting an evaluation for. People are trying to better understand what OpenSpace is, how the public interfaces it, and whether or not you enjoy cool programs like this. So we are going to include a URL a little later in the program. We would encourage you to go to that URL, check it out, fill it out, and let us know what you think of this program and the software. So looks like my super producer Bing has put that link right in there for a Survey Monkey. You can check it out and let us know. Now, we are right now floating around in space next to the thing that gives our wonderful solar system its name. Solar system is our star, the sun. When we talk about our solar system's past, present, and future, they are very closely linked to our star. It's kind of the boss around here, makes everything else happen, or wipes everything else out. Now, when we talk about a star, we often call it alive. And that's a little bit of a fault on the part of astronomers. We like sympathizing with these things we study, but there's an unfortunate tendency to anthropomorphize, which is a dollar word that basically means make it more like a human than it actually is. Stars aren't alive. A star is a giant collection of hydrogen, little bits of helium, depending on the star. They use up that hydrogen over the course of their lives to make energy. That energy shines out into space after spending a long time traveling through the various layers of the star. But as that energy shot out, there's not an infinite source of energy in our universe. So eventually a star runs out of juice. And much like a carbon-based life form here on planet Earth, it's got a beginning, a lifetime, and an end. So we use those terms like life. While it's burning and using that energy, it does have a lot to do with. It seems very similar to the thing that we call life. And when a star is born, again, using that kind of anthropomorphizing word, when it comes into being and begins to shine, turns out a side effect of that birth is sometimes planets. Now you can see our solar system here. These blue orbits are showing you the position over time of the planets of our solar system. That closest blue line is where Mercury travels. So the end of the line is where Mercury is, and the fading out distance behind it shows you where Mercury was. You can see a similar line for Venus, Earth, Mars, and as we head back, Jupiter, Saturn, Uranus, and Neptune. Just remember, my very educated mother just served us nectarines, and that's the first letters of all of our planets as a mnemonic. So looking at the distribution of planets around our sun, I'm going to see if I can get this nice and lined up. You can see our solar system is almost perfectly flat. Not quite. I can't get all those lines exactly parallel to each other, but I can get pretty close. Now, why is that possible? We have every reason to think that it has to do with how our solar system was formed. At the beginning, when our sun was very first getting started, all that material was pulling in towards the sun. There was a disk of material wrapped around it. And in that disk, things began bumping into each other, sticking together, and that's where planets formed. Now, because of that, all of our planets travel around the sun in the same direction. They don't all spin the same direction. There are some weird ones out there, but we travel around the sun in the same direction. We think that a lot of other solar systems form in a similar way, but that's something that we are currently studying by pointing our telescopes out in other directions away from our star. And this has led to some pretty cool observations that we call the extrasolar, or exoplanets for short. And there are tons of really cool things to see. So I'm going to take a moment and turn some of those on. They should show up as big blue markers, sort of monochromatic Fruit Loops stuck to some of these stars nearby. Yeah, I had it for a second. While I'm trying to get exoplanets to work, if you have something you would like to see inside our solar system or nearby, just drop it in the comments and we will be happy to check stuff out a little later. Now, while we're looking around here, you can see those blue markers. Many of them are concentrated in specific parts of our sky. There are really cool things to see along the plane of our galaxy. Some of these very densely populated fields are coming from the Kepler Space Telescope's ongoing mission to find as many, formerly ongoing mission, to find as many planets as it could around other stars. Why formerly ongoing? Well, its last rotating wheel broke, and it can no longer accurately point, or at least not accurately enough to get us good data. So the Kepler mission is going to be a truncated version of what was originally optimistically aimed at. So you can see a very dense pack of stars with planets around them right there. That is the primary Kepler field of view. I'm going to fade down those extrasolar planets, though. If you have any spot in the solar system you would like to see, please let us know. I'm always happy to take some requests from the audience. Swati suggests Mars. I think that sounds like a fantastic idea. So we are heading out to that fourth orbit from the sun. As we go in, let's get rid of those orbit lines. They're just a little distracting. There we go. As we get closer to Mars, you get to see first and foremost the color. When we see Mars in the sky, it definitely has a reddish hue, and kind of an orangey red color can be seen here. If you're looking for prominent features on Mars, there are quite a few you can spot from even this far away. What are we looking for? Well, some dark dots. You might be able to see some right here on that limb. Those dark dots are showing us the presence of giant mountains or changes on the Martian surface. If we wanted to see them a little better, we get lined up right with the equator of Mars. I'm actually going to kind of cheat and use our super cool software to get rid of nighttime on Mars. And I do that by imagining this side was illuminated as well. You can see here a gigantic volcano. That is Olympus Mons. Now I want to give us kind of the scenic tour. We're going to head right in off the side of Olympus Mons and fly over it. This should look pretty cool. You can see Olympus Mons kind of looks like a giant bump, like Mars bumped its head on something truly gigantic. And you can actually see where the atmosphere is lit up around Olympus Mons, but not above it. Olympus Mons is tall enough that it sticks out of the majority of Mars's atmosphere, meaning it's above the clouds. Now, we have mountains like that here on Earth, but as you get higher and higher up, you get less and less atmosphere above you. Now, we had a request for Valles Marineris. That shouldn't be too far away, and another really cool thing to see. Of all the amazing stuff, really having the universe as your sandbox in OpenSpace, I still think one of my absolute favorite things to do is to drop into Valles Marineris. So thank you, Mary, for a wonderful suggestion. Now coming in here, I want to give us a little bit of motion right along the side. Let's tilt our heads and see if we can get right into Valles Marineris. Now, there is very high resolution map data that my computer is currently struggling to download as fast as possible. If you give yourself a longer time with these things, you will always get more and more detail. There's wonderful topography and mapping that's happened on the surface of Mars. Unfortunately, the more Mars data I bring in, the slower my wife's internet connection goes. But that's the unfortunate part of shelter in place. Zooming along the surface of Mars, you can see those bumps and valleys, rifts and ridges. There's amazing stuff to see here. And if you are a fan, one of our upcoming Friday Cosmic Conversations is going to be with Pascal Lee, who is an expert on Mars and what humans might be doing there sometime soon. Check out our Facebook page to find out about our upcoming events. So as we are moving across the surface, you can see these gigantic rifts and fissures. This is a beautiful place, a completely alien place, though. We don't have canyons like this on Earth. True, we got some really big canyons out there between the karst structures that exist all over Asia, between our Grand Canyon we have here in the North American continent. We've got some big canyons, but nothing like this. From one end to the other, across Valles Marineris, we are talking about a distance of thousands of miles. A good analogy would be that if you put one end of it on California, the other end would reach to the Gulf of Mexico. That's pretty shocking. We just don't have something like that here on Earth. Now, we don't think it formed in the same way either. When Mars was cooling down as a planetary object, we believe there was a rift that opened up between two structures, maybe the beginning of a tectonic plate. But alas, Mars does not have active tectonics today. If you want to see that Valles Marineris structure from above, you get that really beautiful scenic view. This is where we flew in, and we flew all the way almost to the other end, depending on what you call the other end. Turns out astronomers are not good at making those firm definitions. Katie's got a great idea. Let's go check out Enceladus. Now, Enceladus is sometimes not cooperative. Let's give it a shot. We are flying out pretty far, about 1 billion miles from the sun to the planet Saturn. But not to the planet Saturn, to a teeny tiny moon flying around it. Ooh, looks like we've got no Enceladus data on today. But Enceladus is an icy world covered with cracks and fissures. If you'd like to see another icy moon, I've got one a little farther out. And just because we didn't get Enceladus, Katie, let's check out Io 2. Rather than Enceladus, let's go see its next door neighbor around the gas giant Jupiter. So one planet over. Let's go see Europa. Now, Europa and Enceladus are often conflated as similar objects by irresponsible astronomers. Like me, I will fully own that. But the big difference is size. Enceladus is teeny tiny. Europa's pretty big. Europa's about the same size as our moon, just a little smaller. But looking around here, you can see some cracks and fissures on the surface. This is ice too. Now, that icy surface is prone to changing. We've not seen a huge amount of change in the small amount of time humans have had powerful enough instruments to examine the surface of Europa, but there is some. The really exciting thing is finding structures that look like they could have changed in the past. How do you recognize one set of cracks that's changed in the past from one set of cracks that's brand new? Well, it's sort of like a puzzle. If you look at some of these regions for long enough, you can see where maybe this feature and this feature probably were connected, but this feature has popped up in between them. In fact, it's interrupted several lines, but this line crosses it. So by piecing together a sort of history of this surface, we really can begin to understand which features are newer, which features are older, which features have been there for longer and have seen more disruption versus which features are more intact. Using that information, really trying to understand how the surface of Europa has changed, we've come to some pretty shocking conclusions. Last week, we talked about how we have a surface that is dynamic. It's receiving energy, and we said most of that energy is coming from Jupiter. That's probably true, but there's also a significant amount of energy being imparted by the other giant moons that travel around Jupiter. Turns out we've got Europa, which is my personal favorite of the Galilean moons, but we also, that's a cool shot, we also have objects like Io, Ganymede, and Callisto, which count as these massive objects too. Now, the request was to go see Io, and I think that sounds like a great idea. Some people call it Io. If you're a classics major, you're probably screaming Io at your computer. I apologize. The astronomer's name for it is usually Io. Just be glad we don't call it input-output. But when you look at the surface, you can see this very different set of colors, very different types of features. This is a volcanically active surface. There's a lot going on here. I like to say it looks like a pizza. Maybe not that appealing a pizza, but the same sorts of colors, yellows, reds, and whites. This is not a exaggerated color mapping or a false color mapping or even translated color mapping. This is just what the surface looks like. It's a pretty exciting place. Lots and lots of activity where objects have smashed into the surface, but also where we see these volcanic calderas. Now, there are a couple crater sites or likely crater sites on the surface of Io, but very, very few. Most of these round features you see are volcanoes. The surface of Io is incredibly young and very active. There's a huge amount of stuff going on, and ultimately its energy is likely from the same source, those other Galilean moons and Jupiter itself. Okay, so we're pulling out. See some cool stuff. Lara's got a great suggestion. Let's go see Uranus. I'm always excited for people to suggest our outer ice giants because they just don't get enough love. Part of that is the fault of backyard astronomers like myself. It's hard to find them. Even when you point your magnificent backyard telescope at Uranus or at Neptune, the best you can really hope for is a colorful dot. That's it. You're never going to see rings. You're never going to see Maybe moons, I guess, if you had a very powerful telescope or were doing astrophotography, but probably not much more than that. Certainly no cloud features or anything like you can get on Jupiter. That's just a function of distance. When we talk about how far away these things are, they are light hours from the sun. I think about a light hour, maybe a little more. No, Saturn's about a light hour, so these are probably a little bit more than that. When you look at the surface, though, you can see these dark clouds and light clouds. That's a little unusual. There could be a lot of different structures, a lot of different things going on here. You can also see this yellowy region, indicating the presence of different chemical compounds. That's exciting. At the American Geophysical Union, we have one of the biggest gatherings of scientists that ever happens here on planet Earth in San Francisco every few years. It happens in other places too. But while I was there, a student, should say a postdoctorate, who's working on a project as a student to another scientist, asked a very troubling question. What kind of chemistry is happening inside Uranus? What kind of chemistry is happening inside Neptune? The best answer we can give you is we don't know. Chemistry can change with different pressures. Chemistry can change with different chemical compounds there at different temperatures. Even the presence or absence of light can change how chemistry unfolds. When you piece all that together, very different sorts of chemistry could be happening on the surface of Uranus as opposed to well beneath the surface of Uranus. And we just haven't done enough experimentation to guess how that changes or what's going on. We can make some predictions. There's a lot of ideas floating around about what could be going on inside these ice giants, just not a whole lot of actual factual data. Now, every layer above and below has the potential to influence what's going on above and below it. So this immediately becomes a super complicated problem and one we just need to know more about. Understanding an object like Uranus and Neptune is possible, but only if we've done the lab work to really build good assumptions about what's happening here. I see a question or a suggestion from Swati to go visit the Oort Cloud. I don't know if I have any Oort Cloud objects built in, but I can take us to about an Oort Cloud distance. How about that? I'm going to turn on our controls here so we can actually see how far away we are from different objects. Okay, so right now we are at 1.8 AU, or astronomical units, from our good buddy Uranus. We're going to focus on our sun. Now, if you wanted to get to the Oort Cloud distance, that's where our icy long-period comets hang out, how far do you think we have to get? Well, right about here, we're about 4.5 light hours from the sun. You can see that number right up there. Now, that is about the same distance as the orbit of Pluto. I can show you Pluto right there, and I might even be able to turn on our Pluto orbit line to give us a little bit better representation. There we go. There's our Pluto line. Here's our planet lines. Now, let's look back towards the sun, and when I do, let's keep this going. How far do we have to get to the Oort Cloud? Now, beyond the orbit of Pluto, we have our trans-Neptunian objects. We've got our Kuiper belt. There's a lot of things out here. But turns out our Oort Cloud is farther than that. So let's go out to maybe 5 light days. How's that sound? Let's get out to about here. Once we're at 5 light days, this is how far light would travel in 5 days. After blasting off from the surface of our sun, this is how far it gets, 5 days. Let's give it an even light week. How about that? Right to about here. Now, once we're a light week out, are we at the Oort Cloud? Not even close. To get to our Oort Cloud distance, we've got to get to pretty much about 2 light years from our sun. This is where the Oort Cloud would really terminate, where it would start to fade out. Now, 2 light years away, that is a good distance. It's converted to parsecs, but that's just 3 parsecs. So if we get to 66 parsecs, it should be pretty close to about a light year, 2 light years. So from way out here, maybe a hair more because it's 3.27 light years to a parsec. So out here, we are at the edge of the Oort Cloud, which means light leaving our sun travels for about 2 years to get to you. and we're about half the distance to our nearby stars. This is a crazy distance away, so huge that it's hard for us to hold on to an idea of how far light would travel in 2 years. That's wonderful. That's awesome. And that is still part of our solar system because those things are still traveling around us. Ooh, Daniel wants to know about the imagery we're showing you. Where does it come from? Which spacecraft are sending it to us? That is a complex tapestry of really cool ideas. I'm going to ask Bing if you can point my camera back for just a second and give me the full screen mode. I've got a really fun cheat sheet I can show you. Let's check this out. So right up here, you can see the chart of cosmic exploration. There's a nice little key that gives me cheat sheets for which missions travel to which planet. So if it sounds like I really know what I'm talking about, just remember I'm using crib notes. But when we're looking around here, we have the ability to see some of the objects like the moons of Jupiter, thanks to the Galileo mission in a large part. We've received some other imagery from like Hubble, taking great shots, but a lot of that comes from the mission that orbited. When you want to see a really good view of a surface, our Earth-based telescopes just don't provide enough. But for our sun, this is sampled, I believe, from a set of SDO images from a while ago. However, our sun just doesn't look this exciting today. If you were to look at a SDO view of our sun today, it kind of just looks like a yellow ball. Turns out the universe doesn't always cooperate with our super cool up-to-date information. I got one last thing to show you, though, on that score, though, Daniel. But for right now, let's jump over. I saw Faye ask a cool question. Can we see another solar system? I don't think I've got a nice up-close view of a solar system ready to go. We focused a lot on our solar system, but let me see if there's something I can show you anywhere nearby. I don't see anything, just my indicators. But let's see if I can tell you a little bit about a solar system we might see. Well, we have found a solar system called the TRAPPIST-1 system. Now, if anyone lives there, they probably don't call it the TRAPPIST-1 system. We named it that in kind of a silly way because some Belgian scientists, using, I believe, a telescope in Belgium, found a couple planets going around a teeny tiny red star. And then the Spitzer telescope pointed in the same direction and saw about, I think, 5 more planets. But when you added it all up, there was a huge amount of planets in this one little tiny solar system. And when I say tiny and solar system, that's kind of a weird thing to put together. Our solar system is pretty big. But imagine if our sun was a basketball, the TRAPPIST-1 star would be much, much tinier, like a golf ball next to our sun, the basketball. So a little tiny star. And imagine if you had all 7 planets traveling around the star right next to it, within the orbit of Mercury. So Mercury's right here. Mercury is the closest planet in our solar system. In the TRAPPIST-1 system, you'd have all those planets clustered in super tight to this teeny tiny red star. Now, that would be a solar system totally different than ours, but there's something really exciting about that. If you have a very small star, like a teeny tiny red star, a golf ball star, not a basketball star, it doesn't give off as much energy. It doesn't give off as much heat. Now, that would mean that solar system would be a lot colder, right? Maybe, but not necessarily. If you have a small star, being closer to it still gives you more energy. If you ever want to try this out, when we're allowed to go camping again, go camping and move closer to your campfire. You can feel more heat on your face, on your skin. These little planets are so close to their teeny tiny star that they could be receiving a similar amount of energy to what we receive from our bright, hot star here on planet Earth. Now, if you add that idea together, these are small, rocky planets that get about the same amount of energy. Some people think there might be a possibility for life on those tiny Earth-like worlds. That would be super cool. We don't know enough about them yet to say if that's true or if it's not, but they are places we really want to discover more about. Dan's got a great idea. Let's go see our closest neighbor star. Here's the question. What do you define as our closest neighbor star? Now, the standard answer for sure would be Proxima Centauri. How do we know that's the closest? Because Proxima means closest. And you can actually see Proxima, I believe, right? But you can't see Proxima. You can see Alpha Centauri is very nearby. Should be right over there. Yeah. So Proxima Centauri, and then in the Proxima Centauri system, we actually don't just have one star, there are three. And in that, there's a tiny reddish star, and that tiny reddish star actually falls closer to us than any other. That's Proxima. We also have a whole bunch of small red and brown dwarf stars in the neighborhood, but Proxima is the closest. If you want to find out more about these teeny tiny stars, those red stars, check out our cosmic conversation from, I believe, last week. Man, time flies, where we talked to Eileen Gonzalez, who is an expert on brown dwarfs. Will any of the planets in the TRAPPIST-1 system crash into each other since they are so close to each other? Great question, Laura. Why don't planets crash into each other? And the very simple answer is, if they could, they would have already. Between today, when we see our solar system as it is, and when our solar system formed is a relatively short amount of time in astronomical time, 4.6 billion years. Now, that isn't a short amount of time. I lied. By any measurement, that's a long amount of time. And in that amount of time, if two of these planets had a possibility in their orbit to get slightly too close and bump into each other, they would have. When you see a solar system that's survived millions or billions of years, it probably means the orbits are very stable. And specifically, in a system like that, where it is so closely packed, we actually have a really good analog in our solar system, which is Jupiter. So let's head out to Jupiter. Let's look at it from above. And I'm going to try something out. Let's see if I can do our Galilean orbits. Now, check this out. This should be pretty cool. I'm going to freeze our motion stuck to Jupiter. And I'm going to go in and take control of time in our software. Now, I'm going to do that by clicking here. And I'm going to tell it that I want to go forward by, let's say, hours. And let's go forward in time. Can you see our planets going around? Let's go. Woo, that's too fast. 10 hours a second. Lovely. So when Io crosses this orbit line, boom, Europa did too. And now Io has crossed it again, and Europa's only made half an orbit. And by the time they come back, boom, they cross it at the same time. Now, that's not a coincidence. Io and Europa are going around our Jupiter in what we call an orbital resonance. Every one trip around the inner moon makes, the outer moon makes half a trip. So there's a 1 to 2 orbital resonance. Now, you might notice similar patterns with our outer moons. I believe that Ganymede, the third moon, is going to make a quarter rotation for each orbit that Io makes. This sets up a very elaborate kind of synchronicity where the moons are stable. They don't pull on each other in a way that's going to disrupt each other or cause them to collide, because this very elaborate pattern has come into existence over time. And because of that, there are no collisions in the foreseeable future. Mathematically, these resonant orbits are very, very stable, and also part of the reason that paper described the gravitational influence on each other as being a source of energy. Now, I think we are getting very close to our time limit, but Colin's got a question. Are the planets on the same plane, or are some higher and lower than the others? We talked about this briefly. We have a pretty good plane in our solar system, but not perfect. When you look at the planets going around our sun, I'm going to jump us back to now so I don't mess up Earth too much. You can see most of the planets are pretty close. Now, there is one object there you might notice is going very far above and below the plane. It's also got a different color. I'm going to spoil something for you and say that's because it's not a planet. It's a dwarf planet. Turns out both of our dwarf planets are kind of the weird kids at the party. They're traveling well above and well below the plane of our solar system. Our major planets, that's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, all travel very close to that plane, with a couple of them having slightly more eccentric above and below orbits. Now, to jump back to a question we had, I think, from Daniel a little while ago, I wanted to zoom us into this third planet from the sun and show you one last super cool thing. Let's check out the imagery from Earth. Now, pointing a telescope at Earth doesn't give you huge dividend. If you pointed a Hubble at Earth, you wouldn't see pretty much anything. It's not designed to look at Earth's surface. But when you look at Earth in the OpenSpace software, we are seeing not Hubble space imagery, but imagery from the Suomi spacecraft. And because it's coming from Suomi, not Hubble, you get this beautiful high-resolution surface where you can actually see the clouds of planet Earth and how they change. But if I look at Earth right now, Earth looks pretty weird. It looks like somebody trimmed off this half the planet. Well, that's because we are seeing, as of right now, what the spacecraft sees, and it hasn't finished today's map. That's how fresh this data is. It gets updated daily. So if I were to take time and really cheat and go backwards, you could actually see if I went back by, I think, a day. That might be easier right here. Doom. There we go. Now we've got a complete map of Earth because the map for September 2nd, according to GMT, is already done. So in using that, you can see the entirety of Earth's surface in that beautiful and high-resolution way. So we learn a ton about the planets of our solar system, some from spacecraft flying out to them, others from orbiting spacecraft here around planet Earth, giving us as much information as we can about the really cool objects in our solar system. We mostly see planets traveling around the sun, moving that same direction, but sometimes we would see a planet go in an opposite direction with its given orbit, what we call a retrograde orbit, just as Swati asked. So a planet would seem to march backwards in the sky. Now, I think we're at the end of our show, but I'm going to pass the buck and the ball off to Bing. That's an alliterative sentence. If you want to find out more about retrograde orbits, we've got a really cool program tomorrow called our Night Sky Update. And if you want to see why planets move the way they do across the sky, I'd be willing to bet he'd be happy to answer that question. But for me, right now, I would like to thank all of you for joining in and our virtual tour of outer space. Thank you for all the questions and for watching and for letting us share this program with you. If you have the opportunity, we and OpenSpace and NASA would really appreciate it if you can follow the link that we put in our comments. It's a very short survey. You can finish it in just a couple minutes, and we would really, from the bottom of our hearts, appreciate it. From the Morrison team, from OpenSpace, and from all of us, thank you for joining us here for our virtual tour of outer space. Have a wonderful rest of your day, wherever it might take you. Thanks again.